Okay, so in this video, I just want to go through um, how to perform some integral approximations in Python and to visualize them. So, per usual, we've got our standard libraries imported here. I'm telling it to print my graphs in the notebook. Um, I'm going to import and abbreviate pyplot, numpy, sympy, execute that cell. Now, here's the first problem. We want to calculate the left-hand endpoints and right-hand endpoints for f of x equals x squared on this interval from 1 to 3. So all the important pieces are here. There's going to be 6 rectangles. This is what we're going to use to find the height of those rectangles, this function x squared, and they're going to be placed between 1 and 3, equally spaced. There's 6 of them. So the first thing that we can do is I'm going to create variables for each of these important values. The left endpoint, A, the right endpoint, B, and the number of rectangles, N, equals 6. Then I'm going to find the width of the rectangle. So if we execute this cell, now I have these variables stored in there, and I can create another variable, call it width, and that's going to be the width of these rectangles, which is found by the distance of the interval itself, b minus a, 3 minus 1 in this case, divided by the number of rectangles, divided by 6, n. And if we see, what we expect is 2 over 6, or 1/3. That's exactly what we get. Now, we can find where each of these rectangles is located by just continually adding widths to the left endpoint. In the examples of left-hand approximations, we're going to build that first rectangle right at the first left endpoint. So we just start at 1 and we go over no widths. The next one is built at 1 width, then 2 widths, then 3 widths, then 4 widths, then 5 widths. And this is really just saying this is at 1, this is at 1 1/3, and so on. So we can print and take a look. And that's exactly what we would expect. Again, this is 2 2/3, 1/3 right before the right endpoint of 3. You should notice the structure, though, the consistent structure here, right? Each of these terms is just a continued multiple of the width of the rectangles. So this 0, 1, 2, 3, 4, 5, we can automate that. And we're going to build that list using list comprehension here. And all we need to vary is that the factor with the width. So we have 1 plus 0, 1, 2, 3, 4, 5. Well, we know that those are generated. We can generate those using this range function that we first used for some simple loops, and make that list. And then when I execute it, I see the same values as what I got when I did it the long way here. This was kind of the long way, much shorter. And imagine if I, instead of having 6 rectangles, I had 60, which of course we'll do. So here's my set. Now again, what these are is these are the values that the rectangles will be built on. Remember, our curve is f of x equals x squared, so let's go ahead and define a function for that. F of x equals will give us back x squared. And then what we want is we want to evaluate this function at each one of these values. We want to find that height at 1, at 1 1/3, at 1 2/3, at 2, at 2 1/3, at 2 2/3. And again, we can do that by creating a variable called heights and just substituting into this function f each of these values. And that's what this means. It means go ahead and take each of the guys in L6 and pop them into this function. And if we execute that, we see that now at these values, these x coordinates, these are the y values for this function. So now that we have the height of each rectangle and the width we know is the same for each, we can go ahead and compute the area of each individual rectangle. So the areas are just going to be these heights times 1/3 or times the width. And again, we can create a variable, use a list comprehension, and say it's going to be the area of each of these rectangles is going to be the width times, well, this number will be the area of the first rectangle, time the width times this number would be the area of the second rectangle, times this would be the area of the third, and so on. But we're just, again, automating it with saying each of these guys in heights, each of the guys in this list, we're going to multiply by width. And again, we get six values representing each of the areas. So this is the first rectangle, this is the second, the third, the fourth, the fifth, the sixth. And if we want to get a little bit cute, we can write a little loop that enumerates things. So I create a list of rectangles, and then I'll print out the area of rectangle L. This will count from 1 to 6 is, and it will spit out the value of the area. So here we have a statement for each of these. This is not necessary, but I just thought maybe you would like to see it. Now all that's left to do is to add these all together. Again, I'm going to create a variable. I'm going to call it total area, and all we do is sum the areas, and I'll print the total approximation for the area under F with L6 is 7.370,370,370 repeating. Okay, so again, the idea was first what we do is figure out the width. With the width, we can figure out where we're going to find the height by just adding multiples of that width, however many there are rectangles. We can evaluate the function at each of those values. We can then multiply each of those values times the width to find the area of each individual rectangle. And then we add all of those rectangles together to get the total area. Finally, we can take a look at that. I'm going to create a figure. I'll plot L6. Remember, these are the x coordinates, and the heights were the actual value of the heights. I could have done this differently, but these were the heights, and I'm going to connect them with just a dashed line. To make the rectangles, I can use this step function. A step is like a staircase, and so this will form a staircase at L6, those x values, and it will form a staircase at the y values of these heights. And where post means that it's going to step after those values. Finally, I can draw vertical lines with I can draw a vertical line at each of the values in L6, each of those x coordinates, and color them red. And if I execute this, this is the plot I get. So exactly what we would expect. Here's our curve, x squared. The left-hand rectangle, the first one is here, second is here, third, fourth, fifth, and I'm missing my sixth. But we see the picture. I need to adjust something about I just need to get the plot out further, because L6 is, right, I'm missing a value here. L6 only goes to 2 2/3, so that's why we're missing this. You can fix that if you'd like. All right, the last thing we might want to do is to check this with the actual value of the integral using SymPy. So I'll change to symbolic work by declaring x to be a symbol, and I'll just directly input the information into the integrate function. Again, I'm integrating x squared from 1 to 3. This is going to tell me the real value of that integral, 26/3. And what I can do is I can see how far off I was based on the total area. The difference between that value and the total area is about 1.3. So, you know, with only 6 rectangles, we were 1 3/10 off about. Not too bad. But of course, we want to increase the number of rectangles. So what we can do is we can automate our code that we've used to this point, right? Here was everything kind of put back together. And I think that we can just change a couple of things here and get a better approximation. So for example, let's change n to be, now instead of 6, maybe we can do 60. Width will stay the same. We're still on the same interval. Now instead of 6 times, though, let's actually change this. We can change this instead of directly referencing 6. It's going to be however many rectangles there are. So, and I'll call this variable L60 now. Here, this is L60. And we should have everything else together. And okay, now we get 8.53. So that changed quite a bit. And if we want to compare that to what we got with SymPy, then again, we can do psi dot, 26 over 3 minus 8.534, and we've decreased our error significantly. Now I can even just change this now to 600, and 8.653, let's now see what total area, and even better still, what about 6,000? Better still, 60,000, better still. You get the point. All we have to do is just change n, and everything updates. It's a beautiful thing. Hopefully you can compute the area of the right limits now, and what will change is where you're finding this, because it's not going to be, the first rectangle is at 1 width, not 0 widths. So you'll have to adjust this piece in order to get those right approximations.